Hi guys, and welcome back to my channel. In this video, I want to talk about periodic trends, and we'll mainly be focusing on the exceptions to periodic trends. You should have learned the general trends in an AP chemistry class or just a general chemistry course. So I really want to talk about the key exceptions that you need to know for the Chemistry Olympiad and just in general. So just as a review, I just have a little diagram showing the general trends. As you can see, electronegativity increases as you go to the top right of the periodic table. Ionization energy also increases as you go to the top right. Same with electron affinity, and atomic radius is opposite of that. You should have learned all of this in AP Chemistry, so I'm not going to really spend any time on this diagram. You should review this if it doesn't look familiar. Okay, so what are some exceptions that we need to know for periodic trends? Useful exceptions generally arise from these two main properties. We have two main properties where exceptions arise, and you should sort of be able to reason these exceptions out. So we have the fact that half and fully filled orbitals have special stability. So what do I mean by half and fully filled orbitals? Say I have nitrogen, for example. And if I draw out the electron configuration for nitrogen, we have helium, and we have 2s2 and 2p3, right? So if I look at my valence electrons, I have 2s2 here and my p orbitals. So I fill up my s orbitals, and for the p orbitals, when I fill it up, there's only 3 electrons in nitrogen. So they are all paired and in different orbitals. And this is a key thing, right? This is a half-filled orbital, which is unusually stable. So there's a special stability with half-filled and fully filled orbitals, and this is going to cause some of the exceptions that we see. Another key property that arises or that causes these exceptions are electron-electron repulsions. So say we have a small atom, right, like fluorine, for example, and we're looking at the electron affinity of fluorine. So I'm adding an electron to fluorine. What's going to happen, right? Because this fluorine is such a small atom, we have the electrons really close together in the atom. So when I add an electron, there's going to be really large repulsions because the electrons are sort of confined to this smaller space. So these electron repulsions are going to cause some unusual exceptions to electron affinity and to other trends. Basically because the small size leads to electrons being closer together, which leads to stronger repulsions, which is less favorable. So we're going to have a higher energy. Okay, so now let me talk about the exact ionization energy exceptions and electron affinity exceptions. And these all basically arise, as you can see that I've written here. These ones arise from half or fully filled subshells that are extra stable. So let's just look at a few of them. Let's look at boron and beryllium, and I really advise you to have a periodic table so you can look at these for yourself. But if we see boron, right, boron, what the electron configuration of boron is helium 2s2 2p1, whereas beryllium looks like helium 2s2. So this is beryllium, this is boron. So we can see that beryllium has a full shell, right? It has a full s subshell, whereas boron has the full s subshell, but sort of has this extra high energy p electron, because p is higher in energy than s, right? And because of this extra high energy electron, it's actually going to be easier to rip off this electron from boron than to rip off a valence electron from beryllium, where our ionization energy trends would say otherwise. So this is an exception, where the ionization energy of boron is less than that of beryllium. And there's really similar, an exception for aluminum and magnesium, which is just in the period below. Now if we look at ionization of oxygen and ionization energy of nitrogen, we see the same exact trend. And why is that? If we look at oxygen, what is the electron configuration? We have helium 2s2 2p4, and with nitrogen we have helium 2s2 2p3. And when we drew our nitrogen shell up here above, we saw that nitrogen has a half-filled subshell, which is pretty stable, right? Whereas oxygen has this half-filled subshell, but if I draw this as oxygen now, there's an added electron there. So if we remove this electron from oxygen, we'll be creating a half-filled subshell, which is stable, which is more stable. Whereas if we're removing an electron from nitrogen, we're taking this half-filled subshell and we're sort of breaking that stability. So what this means is that our ionization energy of oxygen is actually going to be less than that of nitrogen, because it's going to take more energy to remove the electron from the nitrogen because of how stable the half-filled subshell is. So this is an exception where we have ionization of energy of oxygen being less than that of nitrogen. And we can see there's an analogous exception with the period below where we have sulfur and phosphorus. Now I want to talk about electron affinity exceptions, and these are exactly the same, basically, as the ionization energy exceptions. If we look at beryllium now and lithium, right? So let's look at beryllium and lithium. Beryllium has the electron configuration helium 2s2, whereas lithium has the electron configuration helium 2s1. So what is going to be easier to shove an electron into, basically? The higher electron affinity means it likes to grab on an electron more. So if we shove an electron into beryllium, what we're doing is we're adding an electron to the p orbital. We're adding it to the 2p orbital. Whereas with lithium, when we're adding an electron, we're making this helium 2s2. And remember that we said fully occupied subshells are more stable, right? So with lithium, we have a fully occupied subshell when we add an electron, whereas with beryllium, we're adding an electron to a higher energy level, the p energy level. And this makes it more unfavorable, which is exactly why the electron affinity of lithium is greater than that of beryllium. So this is an exception because our general electron affinity trends would say otherwise. And we can see this exact same exception with magnesium and sodium, which is on the period below. Now I want to talk about nitrogen and carbon, which is exactly basically the same as when we talked about oxygen and nitrogen ionization energies in the previous section. So if we look at the nitrogen electron configuration, we get helium 2s2, 2p3, and carbon looks like helium 2s2, 2p2, nitrogen and carbon. So when I shove an electron into nitrogen, again, I'm breaking this half-filled stable subshell, and I'm breaking that stability. Whereas if I add an electron into carbon, what am I doing? Right now, this basically is carbon, where I have these two electrons in my p orbital. When I add an electron into carbon, I'm forming that half-filled stability. So what does that mean? That means my electron affinity of carbon is going to be greater than that of nitrogen, because when I'm adding an electron to carbon, I'm forming that half-filled stability, whereas when I'm adding an electron to nitrogen, I'm removing that stability. So carbon is going to want to grab onto electrons more than nitrogen, and that's what we see in this exception, where we have the electron affinity of carbon is greater than that of nitrogen. And again, we see an analogous thing with the period below, where we have the same thing with phosphorus and silicon. And the last thing I want to talk about is the electron affinity exceptions that come from electron-electron repulsions. So this is a different sort of category, a different category of properties that causes the exception. So let's look at oxygen and sulfur, and fluorine and chlorine. So if I add an electron to fluorine, because it's so small, right? Because fluorine atom is so small, these electron repulsions, the electrons are so close together that there's going to be really strong repulsions. And this is going to cause a super high in energy sort of fluoride anion when I add an electron to fluorine, comparatively. Whereas if I add an electron to chlorine, the electrons are farther apart because chlorine is a bigger atom, so we have less strong electron-electron repulsions, and this sort of keeps the energy low, which is what we want. So this means that the electron affinity of chlorine is actually going to be greater than that of fluorine. And the same thing happens with oxygen and sulfur. If we add an electron to oxygen, because oxygen is such a small atom, right, the electrons will be close together and there'll be strong repulsions. Whereas if I add an electron to sulfur, it's a slightly bigger atom, so the electrons are slightly farther apart, and there's going to be less strong repulsions, meaning that our sulfur anion will be lower in energy, meaning that sulfur would grab electrons more readily than oxygen will grab electrons. And that's what we see here in these exceptions. Okay, so now I just want to talk about the inert pair effect. And this is sort of a periodic trend that's not really covered generally. And this is just the tendency to form ions 2 units lower in charge than expected from the group number. And this is generally observed for larger atoms. So let's talk about why this happens, right? Big atoms have really low energy s electrons because the s electrons are good at penetrating to the nucleus. They're good at getting close to the nucleus and staying at a low energy. And there's poor shielding by d electrons. What does that mean? That means the d electrons don't really repel the s electrons. They don't really cause a repulsion, and instead the s electrons are very attracted to the nucleus. They're very penetrating, they're very stable, sort of close to the nucleus and happy. They're low in energy. So basically, what does this mean? Because the s electrons are very happy and close to the nucleus, they don't get removed as easy as you think they would, right? They don't get removed when you form ions as much. So let's look at some examples. We have indium 3+ and indium plus. They're both prevalent. Why? Because this indium is not very affected by the inert pair effect because it's not a huge atom, right? It's not a huge atom where the s electrons are super low in energy comparatively. Whereas if we look at lead and tin, right? Lead and tin are in the same group, but lead is a bigger atom than tin. So what we would think is that lead is much more affected by the inert pair effect because the s electrons are much lower in energy. And this is exactly what we see. We see that Pb2+, lead 2+, is much more prevalent than lead 4+. So Pb2+, much more prevalent than Pb4+. And why is this? It's because losing those 2 s electrons, which is needed for Pb4+, is not favorable because they're so low in energy. So our Pb2+ is going to be much more favorable, and that's what we see. We see Pb2+ much more in nature. Whereas with tin, we see the opposite effect. We see Sn2+, Sn4+ is much more prevalent than Sn2+. Why is this? Because tin is not affected by the inert pair effect because it's not a super big atom. And because of this, the s electrons are not super low in energy, and it can lose the s electrons, forming the 4+ cation. Whereas the 2+ would be if they didn't lose the s electrons, which doesn't happen because it doesn't happen as much because the s electrons are relatively high in energy. They're not super low in energy like with bigger atoms like lead. So now I want to talk about diagonal relationships, which is not really an actual trend, but rather sort of an observation. And it's basically that diagonal related pairs of elements show similar properties. And how can we sort of reason this? Let's look at lithium and magnesium, for example. If we see lithium and magnesium, lithium has an n equals 2, right? That's the n equals 2, that's the second period. And magnesium is in the third period. But magnesium, right? It's a little bit larger when we look at only the periods, because as we go down the periods, there's more shells, right? Our n shell gets larger, and that means that there's more electrons, so it's a slightly bigger atom in general. But we go to the right as well. And what does this right do? When we go right, there's a higher effective nuclear charge. So what does that mean? These two sort of opposing things kind of cancel each other out. So one element has a higher valence principal quantum number, right? We see our magnesium has n equals 3 versus n equals 2. But that element also has a higher effective nuclear charge. Magnesium has a higher effective nuclear charge because we're going to the right in the periodic table. So these two factors kind of sort of cancel each other out, and the properties of the two elements are very similar. So how exactly do we see this, right? What properties are similar? If we look at lithium and magnesium both react with nitrogen to form nitrides. So for lithium, we form Li3N, and for magnesium, we form Mg3N2. And these are sort of the only two metals that will sort of react with nitrogen to form nitrides. That's a common property we see between lithium and magnesium. We also see this diagonal relationship with beryllium and aluminum. These they react with both acids and bases. So they react with both acids and bases, and that's sort of a interesting property that we see with beryllium and aluminum that are diagonally related. Now I want to talk about the lanthanide contraction, which has to do with atomic radii and shielding effects of F electrons, hence lanthanide, right? This has to do with F electrons because we're looking at the lanthanides. So what is the lanthanide contraction? The atomic radii in the third row of the d metals are about the same as the second row d metals. So generally when we go down in row, we think that there's a higher valence principal quantum number, which means that generally that the atoms should get bigger, right? But these two in the third row and the second row have about the same size. So they're smaller than expected, right? The third row are smaller than expected because they're expected to be larger than the second row. What is this? Why is this happening, right? Basically, we have an increase in nuclear charge across the period, right? And we have poor shielding of F electrons, causes the d electrons to be pulled even tighter, and for the atomic radius to be smaller than expected. So what exactly does this mean? When we're looking at this third row of d metals, we have a huge increase in nuclear charge from the second row d metals, right? Because there's much more protons in the nucleus, but also because of these lanthanides with F electrons, we have really poor shielding by the F electrons. That basically means that the F electrons don't block out the nucleus's effect, and the high effective nuclear charge causes these d electrons to be pulled really close to the nucleus. So the d electrons are pulled really tight, and due to this, the atomic radius is smaller than expected. So the second row is basically equal to the third row in terms of a size. And what does this lead to? This leads to super dense metals, right? If we think about this, we have third row d metals that are much more packed with protons and neutrons than the second row d metals, but they're literally the same size. So what is this going to mean? This is going to mean they're going to have the same volume but way more mass. And this leads to very dense metals like iridium and osmium. So these are two examples of super dense metals. They have relatively small atomic radii because of the lanthanide contraction, and much more mass than the second row d metals because of all of the protons and neutrons that have now accumulated in the nucleus compared to the second row d metals. Now I just want to discuss some weird electron configurations, and you shouldn't really memorize all of the weird ones. I just want to give some reasoning to why there are some notable weird ones and why the notable weird ones happen. So here in the first bullet point, I just list out the notable weird ones, and you can see there's a little bit of a pattern. Chromium, we have argon 3d5 4s1. Copper, we have argon 3d10 4s1. Molybdenum, we have krypton 4d5 5s1. Silver, we have krypton 4d10 5s1. So you should see a little bit of a pattern where we have our one electron that's supposed to be in our s orbital is sort of being promoted to a d orbital. And we can see that for these exceptions, the main thing to remember is that filled or half-filled d orbitals are favorable. This is similar to what we talked about with the p orbitals with the nitrogen and how it's stable to be half-filled. The same thing happens with d orbitals. So the filled or half-filled d orbitals are favorable. So let's take chromium, for example, just as one example. What we would expect, if just like filling the electron configurations normally, looking at the periodic table, we would expect argon 3d4 4s2. But what actually happens is that one of these s electrons that we think is in the s electrons goes to the d electron. So this becomes 3d5 for s1. And why does this happen? This happens because our half-filled d orbitals, right? Their d orbitals in total can have 10, but the half-filled d orbitals is much stabler than having 4 electrons in the d orbitals. And this additional stability causes our electron configuration to be not what we automatically expect. And this same exact thing happens with copper, molybdenum, and silver. So all of these can be easily reasoned with this same logic. I just want to note that there are several other weird electron configurations as we get to heavier elements. And this happens because the orbitals start to have really, really similar energies, and it's kind of difficult to reason why the electrons are placed in the orbitals that they are. So we won't really talk about the heavier elements, and it's very difficult to reason them. Basically, in all these cases, an electron we expect to be an s subshell, so I'm just reiterating, is instead in a d orbital in order to make a filled or half-filled d subshell, because these filled or half-filled d subshells are exceptionally stable. Okay, thank you guys so much for watching. I hope you enjoyed this video, and I hope it was informative. Thank you again for watching, and I'll see you in the next one.